Hi, everyone, and welcome to today's webinar. I'm Michaela, and we'll be discussing Kubernetes Persistence 101. Today's presenter is Oleg Chunikhin, CTO at Kublr. If you have any questions during the webinar, please post them in the chat, and we'll address them during the Q&A at the end. All right, let's go ahead and get started.
Hello. Yes, Michaela, thank you for the introduction, and welcome to all our attendees. Thank you for joining. So, I'm still at Kublr. We at Kublr work on a system called Kublr as well that is intended to provide Kubernetes management platform for enterprises. And as such, we often help our customers with not only Kubernetes management, but also helping them figure out what Kubernetes is and how to use it efficiently and effectively. And so it's often essentially comes down to talking about Kubernetes capabilities and we essentially started doing a number of webinars that explain various facets and aspects of Kubernetes and cloud native application management. And this webinar is one of this series talking about persistence and managing essentially raw data in Kubernetes clusters. So just as such a basic topic, it is not really specific for Kublr. This information and what we're going to talk about today is applicable to pretty much any Kubernetes cluster, of course with different vendors and in different environments, different clouds. Some aspects of these presentations and demo may behave differently, and we'll talk about that in more details. But the power of Kubernetes is that it provides a very convenient to use layer of abstraction on top of your infrastructure. And that's exactly what we are going to talk about today as it applies to persistence management and Kubernetes. And I'll start with a short explanation of the basic concepts and objects used in Kubernetes for persistence management and for data management. But before going there, so we are not only going to see slides today, so we are also going to go through a short demo that illustrates at least some of those concepts. And so before going into persistence management and abstract concepts, let's take a look at our demo environment setup. So what I did here, I created a couple of Kubernetes clusters running in different clouds. And again, so this is a Kublr interface. We used Kublr to provision those Kubernetes clusters. But so after those clusters are provisioned, they're pretty standard. So the same demo I'm going to show today is applicable to any other Kubernetes clusters, whether it's provisioned using Azure AKS, AWS EKS, or self-hosted on-prem. So I used two different clouds, one Azure, another AWS, to provision those clusters to illustrate where those Kubernetes concepts are similar when you're working with different infrastructure and where they deviate from each other. So we'll talk about that a few more details a bit later. Now, having said that, we will run a few scripts in this demo, and all those scripts and manifests are available on our GitHub account, GitHub Kublr. You will find this Persistence 101 demo there, as well as a number of other demos which may be interesting if you want to look deeper into various Kubernetes topics and aspects. In particular, very applicable to the topic today is, for example, demo called Hybrid Demo, which looks at self-hosted cloud-native storage in much more details. So in that other demo, we're provisioning Ceph clusters in different clouds and set up data mirroring, data replication between those clouds, and show how you can use Kubernetes to implement advanced data management operations like snapshotting, volume cloning, replication, etc., etc. But yeah, going back to our presentation today we are just going to talk about basic concepts and some simple illustrations of those concepts. Okay, so let's talk about how application in Kubernetes behaves in regards to data. So you may be aware, if you are working with Kubernetes already, that when you run a Kubernetes cluster, to manage applications running in that cluster, you create and update Kubernetes resources. So anything is a resource in Kubernetes. Each resource provides its own semantics. So for example, there is a resource called namespace. So namespace is essentially a bucket for other resources. And usually you deploy one application per namespace, or you deploy a group of connected applications, for example, microservices, into the same namespace. Pod is another example of a resource in Kubernetes. Pod essentially represents a unit of compute. So pod combines one or more containers, and those containers run on a certain node of that Kubernetes cluster. They run together, they are started together by Kubernetes, and when pod is decommissioned, they are stopped together by Kubernetes. So pod, as you may guess already from this description, has quite an extensive internal structure. At the very least, pod contains a set of containers. Now, where it relates to storage management, Kubernetes provides a set of resource types that allow you to specify what data a certain pod is going to consume. And those resource types start with a volume sub-resource inside of the pod. So volume is essentially an abstraction inside of the pod resource that describes which external data should be consumed by this pod. And as you can see, you specify that volume as a part of the pod specification, and there, inside of that volume object inside of the pod specification, you essentially specify parameters of the external actual storage that this pod will consume. And that may be, for example, an external cloud disk, like EBS disk on AWS, or Azure disk if you are running on Azure, or NFS share with that NFS share IP address and path which will allow Kubernetes to attach that NFS storage when this pod starts, etc., etc. So Kubernetes supports a number of disk types out of the box, and it also provides you with a pluggable architecture that allows you to support more types using various plugins. So those plugins usually, not usually, but always in modern Kubernetes use CSI interface, cloud storage interface. So this was the very simplistic way of defining what storage your pod is going to use. So essentially embedding the definition of the pod of the storage in the pod specification. As you can see, the pod specification contains directly the actual storage reference. There is also a way to dereference that, to make it more manageable, to separate roles for managing resources. So, for example, it is a common pattern in Kubernetes administration that you have separate roles for developers and DevOps who have only access to certain namespaces. You have a separate role for infrastructure operation teams who may be cross-cluster, may have cross-cluster administrative permissions. So to make sure that those different roles don't overstep their bounds where it relates to storage management, and also to provide a number of other advanced scenarios for storage management, Kubernetes introduces a few more resource types, specifically storage class, persistent volume, and persistent volume claim. So using these resource types allows you to decouple essentially storage administration from storage consumption. And how it's done. So first of all, you or the administrator can create a resource called persistent volume, which now contains reference to the actual storage. Then when this storage needs to be used by a certain application inside of the cluster, developers or DevOps users create a object called persistent volume claim that contains a reference to persistent volume resource rather than to the actual storage. So now namespace doesn't contain any sensitive information or any direct configuration information about actual storage coordinates. So this volume claim becomes essentially a representative of this actual storage inside of this namespace. And now at last you can start a pod which, just as usual, contains a volume which, unlike in the previous slide where we had direct reference to the actual storage, unlike that, now this volume contains a reference to the volume claim in the same namespace. And then Kubernetes knows that this pod needs to get access to this storage. So this, again, as I said, adds flexibility, allows you to manage access better. It also enables automatic provisioning scenario, which we will discuss in a couple of slides. Now, as I mentioned already, there are different types of actual storage that are supported out of the box. And those include things like AWS EBS, Azure disks and file systems, GC disks, CEF file system exposed by CEF storage system, etc., etc., etc. So out of the box, Kubernetes supports NFS, iSCSI, APIs, and many others. And hundreds of other more niche storage types are supported using plugins for Kubernetes that are called CSI drivers or Flex drivers, but Flex is considered, it's not deprecated per se as far as I remember, but it's considered best practice to use CSI drivers if they are available. So all those types of storage can be used both directly from pod or via this persistent volume scheme. There are two types of storage that is called host path and local. Both refer to local file system on the worker node on which this application currently runs. There are two different types. They are supported in different scenarios. So host path can or has to be consumed through persistent volume claim chain, while local can be used directly from pod. Then there are 4 more types of storage, more like virtual storage, that can only be defined inside of the pod. They cannot be defined as a separate persistent volume in your cluster. And those are special types of storage that allow you to supply pod with an ephemeral temporary storage or provide certain meta information or additional information to your pods. So you can map certain cluster metadata onto virtual storage that you provide to the pod, or you can give pod ephemeral temporary storage using these storage types. So now, having seen these different types of storage consumption, I want to mention storage lifecycle. So first of all, when we talked about consuming storage from the pods directly, this only allows very simplistic lifecycle. So storage has to be provisioned outside of the Kubernetes clusters, usually by the administrator. Like, for example, an administrator can go into AWS console and create an EBS disk there. Then the administrator gives developer the disk ID, maybe credentials to access that AWS account where the disk is provisioned, or it's actually, it has to be in the same AWS account where the cluster runs, of course, for the node to be able to attach that disk. And then the developer includes that information into the pod specification. So Kubernetes can attach that storage and provide it to the pod. So this is very inflexible, difficult to manage, etc., etc. So persistent volume and persistent volume claims allow you two other approaches that are called static provisioning and dynamic provisioning. So with static provisioning, and we already discussed that a bit, administrator still can create a storage in the cloud, for example, and then create a persistent volume in the Kubernetes cluster that maps to that storage. And then those persistent volumes can be consumed through persistent volume claim resources created inside of the cluster by DevOps teams or administrators as well, depending on their access level. And the last storage lifecycle, which also uses persistent volumes and persistent volume claims, is called dynamic provisioning. In this case, administrator doesn't create actual storage. Administrator just configures a so-called controller inside of Kubernetes that can create actual storage in response to cluster users creating persistent volume claims. And we can go through these life cycles. So when it's pod volume life cycle, it's very simplistic. We have an actual storage, we start a pod, and Kubernetes attaches this storage to the pod. So with static provisioning, again, administrator creates actual storage, administrator creates persistent volume, then user who has access to a specific namespace creates a volume claim, which then is automatically bound by Kubernetes to one persistent volume if valid persistent volume is found. And then again we start a pod which consumes that storage through that persistent volume claim. Dynamic provisioning is a little bit different. So administrator creates a storage class, and storage class resource describes whole class of storage or a whole storage type. For example, you may have a storage class which can create EBS volumes on AWS of type IO2, right? But you don't yet create those volumes per se. So you only, or administrator only creates this storage class resource that specifies some parameters for those EBS volumes creation. Now, when a user wants to use a storage, the user creates a persistent volume claim in their namespace that refers to a specific storage class. And now a special component, usually running inside of the same Kubernetes cluster, this component is called provisioner, notices that, hey, a new volume claim was created pointing at this storage class, which means that it should actually create the actual storage EBS disks based on configuration parameters inside of that storage class and that persistent volume claim, and then automatically create a persistent volume corresponding to this actual storage, and then bind that persistent volume to this persistent volume claim. After which, as usual, we can start a pod which consumes this storage. So the benefit of this approach is that users who don't even have administrative rights, permissions, can still create storage on demand when they need it within the limits or constraints defined by the administrator. There are a few more scenarios that we can discuss, but before going there, so let's illustrate it. Let's go and run a few demo scripts and scenarios. So as I said, we already have our two clusters running there here. I have my console set up and ready. Let's see. I have a couple of aliases for kubectl configured to work with different clusters. So KWS, it's essentially a kubectl that uses AWS cluster kubeconfig. So for example, if we run AWS get nodes, we will see that here are our AWS cluster nodes. KAZ is kubectl alias for Azure cluster, and if we check its nodes, we see here a different set of nodes. Now, the first thing I want to do, so let's open dashboards, Kubernetes dashboards into those clusters. Kubernetes dashboard is a relatively simple user interface that allows you to see all those resources inside of the cluster. So for example, this is AWS cluster dashboard. You see I don't have any pods running there in my default namespace. We can check if we have any storage classes, and we do have a couple of storage classes there. There is a standard storage class provisioned by Kublr called Kublr system, which points at storage type specific for this cluster type. So for example, for AWS, you can see that this storage class is AWS EBS for EBS disks of type GP2. Another storage class here is NFS, and if you want to check this demo later, you will notice that when we provision this class, those two clusters are actually a little bit different. Of course, they are running in different clouds, but another difference is that for AWS cluster, we also included a few additional cloud resources here, specifically an EFS file system, and we included EFS auto-provisioner controller into this cluster, so that now applications running in this cluster can provision NFS shares under that EFS file system. If we check the dashboard of our Azure cluster, we will see a similar picture, but without EFS storage class. Just to show you how an environment inside of different clusters can be a little bit different. So let's run a couple of demo scripts. So first thing first, we will take a look at a couple of storage classes that I want to create in both of these clusters. And we have here these two classes. So one storage class that I will create in AWS is called, actually for AWS we will create a couple of storage classes, and you will notice that they differ in the configuration parameters, which we can discuss in a few minutes in more details. So one class is called EBS immediate retain, and it's called this way because it has a retain reclaim policy, and it is allocatable immediately. EBS wait delete storage class, on the other hand, has a reclaim policy delete, and it has a different binding mode, which is wait for consumer. And we'll see the difference between these classes in a few seconds when we try to use them. Now, Azure storage class is a bit simpler. So first of all, we just create one storage class called AZDisk, which will provision standard LRS managed disks. So now to actually provision them, I'll run a couple of apply commands. I'll run storage class manifest apply for AWS cluster, and you can see two storage classes were created. And I will run the same similar command to Azure cluster, and I will create AZDisk storage class. So now we can check it in the storage classes. Here they are, our two new storage classes. Similarly, in Azure, we see AZDisk storage class. Now we'll test dynamic provisioning. So we have a couple of scripts to demo dynamic provisioning. PVC dynamic AWS and PVC dynamic Azure. Let's take a look at AWS. So here, what we create a few objects. We create persistent volume claim, first of all, which, as you can see, points at EBS immediate retain storage class. And we create another persistent volume claim, which points at EBS wait delete storage class. In Azure disk, or in Azure cluster, we will create just one persistent volume claim, because we only created one storage class there. You may notice that this persistent volume claim has a resources section, which actually tells Kubernetes cluster what size of the storage this persistent volume claim describes. And this information will be used by the controller inside of the Kubernetes cluster to actually allocate the storage. Now let's run these scripts. So I'll run both commands at once. I will create persistent volume claims in AWS and in Azure cluster. Let's see. So our storage classes didn't change, of course. They are just there. They provide information. But for persistent volume claims, we now see two new objects created in this cluster. We see one persistent volume claim called PVC, which is already bound. And we see another persistent volume claim, which is called PVC wait delete, and it is in a pending state. And we'll see what it means in a few minutes after we actually start pods using those persistent volume claims. We can also check actual persistent volumes in that cluster. And now you notice that for our claim named PVC, a new persistent volume was created, and we can take a look inside, and we will notice that it has already a valid EBS ID, which means that Kubernetes already went to AWS API and actually created this persistent volume. And after creation, it bounded it to the persistent volume claim, so it's completely ready to use. Similar situation we should see in Azure. In Azure, we also see our persistent volume claim, and persistent volume has been already created for that persistent volume claim. And if we take a look inside and check its specification, we will see that it's a little bit different structure, but it also has a reference to the actual Azure disk inside of that specification. Okay, now next step is to actually start pods, applications using that. And for that we have manifests called pods AWS and pods Azure here in our project. Let's open them. Let's take a look. So pod AWS, we create two pods, one for each persistent volume claim. And those pods are quite simplistic. So they just run a shell script which sleeps forever. And not sleeps forever, it's actually forever prints current time and the size of the storage it attached, and lists the content in an infinite cycle. The most important part here is, of course, this part, specification of the storage used by this pod. We are telling Kubernetes that we want that storage attached and mounted to the path/wall inside of this pod. And we are telling Kubernetes that we want to use this persistent volume claim we have just created for this storage. And the same is here. So this part is not different for this pod. The only different thing is that we are using a different persistent volume claim. Now you remember that our persistent volume claims in AWS clusters are in a different states. PVC is ready to be used and PVC wait delete is in pending state. So does it mean that it prevents us from actually starting those pods? Not really, because let's start those pods. Pods are created. Let's check what's happening there. What's happening with this persistent volume claim. Now magically this persistent volume claim that was waiting becomes bound, and persistent volume claim is now bound to an actual persistent volume that was, as you can see, that has just been created. So what happened? The following happened. When we started those pods, so for this first pod, which was going to use the PVC that was already bound, nothing was complicated actually. The storage was ready and waiting for this pod to consume it. Now, the second pod wanted to use this PVC, which was in pending state, and it was in pending state for a good reason, because storage account associated with that persistent volume claim has this parameter called volume binding mode set to the value wait for first consumer. So until there is actually a pod that wants to use this storage, this storage wouldn't be provisioned with this parameter value. And this is very useful when you have availability zones and zone local storage in your clusters. Imagine that you have AWS cluster running across two availability zones, A and B. And when you provisioned your storage was provisioned in a zone A. But when you start a consumer pod, all nodes in that cluster running in the zone A are already filled with pods, and all resources are used up there. So Kubernetes cluster cannot put a new pod into zone A in effect. It would have to put it into zone B, and if it does, the pod won't be able to attach the EBS across the zones. And for situations like that, you can use this volume binding mode wait for first consumer, because with that, the EBS wouldn't be yet allocated. It would only be allocated after the pod is placed onto a specific node into a specific zone. In our Azure cluster, we have exactly the same picture. Our pod started and attached the storage and is using it right now. Another example, you remember that we, when we looked at different storage types, we saw here storage types that are sort of virtual, that are only allowed to be used from the pod specification. So in our examples here, we have an example of such pod called pod CMS. So this shows how we can create a config map in a Kubernetes cluster and attach it to a pod path as such a virtual storage. So this is useful when you want to provide configuration information, configuration file as a part of the Kubernetes resources. So let's run this manifest. Let's try to create those pods and see how it works. So, okay, as you can see, in each of our clusters, config map was created and pod was created. So we can take a look how it works. So we can check config maps. Here's our config map, which has just been created. It does contain this config YAML key with content. Now our pods, we also have a pod running there, which was created, which has just been created, and it maps this config map as a disk. And what does it mean that it maps it as a disk? So we can go and run a console inside of that pod. If you remember, we mapped it to the wall path. So let's go there. You see that this directory is mapped there. And what's inside? Inside, we actually have a file, or you can see that it's a link pointing at the file managed by Kubernetes that contains the same content that is specified in the config map. You can see that by printing that file content. Yes, this is our example config content. So we are more or less done with our demo. The only other example that I have here is an example of consuming EFS storage, and so as you can see, we can use a different type of controllers and pod management tools in Kubernetes to manage auto-provisioned storage. And here this example goes beyond simple pods. So here we will create a stateful set, which actually contains a template for multiple pods, each of which will use a template to create its own volume claim. So, and this is a very powerful concept. So you just have a single object inside of Kubernetes where you specify number of replicas you want to use. And Kubernetes will automatically use this object and use templates inside of this object to both provision necessary number of required number of disks and persistent volumes and claims, and pods consuming those volumes and claims. Let's see how it works. You remember that EFS we only have in our AWS cluster, so I will only apply this manifest to our AWS cluster. Let's see how it works in AWS cluster. Okay, we already have Kubernetes hard at work provisioning storage for the first replica of this stateful set, and it should be ready in a few seconds. We can check what's happening here in persistent volume claims, and we can see that there is a persistent volume claim pending state, which means that, again, controller is trying to create a persistent volume for this persistent volume claim. And as soon as it is done, it will be able to actually mount this storage to a specific pod. And when the first pod is started, it will do the same sequence for the second pod. And when it may take a few minutes, so when it's done, we'll get back here. So provisioning is not the only thing that you, or not the only cycle or operation that Kubernetes allows you to do. So these abstractions, these resources enable you to do many more storage related operations. So you can do volume expansion by just updating your volume claim, and those storage types that support volume expansion will do actual storage expansion automatically, and will update the persistent volume object and the volume claim object to report about the status of this operation to you. And most of the cloud storage types support that. Azure disks support that, EBS disks support that, etc., etc. Although not without specifics, because, for example, EBS disks support full runtime dynamic expansion, while Azure disks require the storage to be reattached. So you will need to restart pods to actually get this bigger disk to see that bigger disk. But other than that, so these abstracts work exactly the same way. Storage deprovisioning works based on this reclaim policy. You saw different values in that reclaim policy. So, for example, by default, reclaim policy, which can be specified in persistent volumes and in storage classes, is delete, which means that when you delete the persistent volume, the actual storage is also deleted, like EBS disk. But you can also use retain policy, which means that when you delete the persistent volume, the actual storage stays. And there are a number of other parameters that you may want to look through when you start working with persistence on Kubernetes and look it up in the documentation. And we have a reference section in this presentation pointing at some documents and documentation pages describing various scenarios and various objects in Kubernetes persistent system. And this slide just lists them all in one table. And you can see that a number of things that you can adjust and customize. Mount points where the storage is mounted inside of the pod, sub paths inside of that storage that you mount that are made available inside of the pod, whether it's read-only or not, mounting, propagation, and mount options for special types of storage, and more and more and more. So I don't want to spend little time we have left going through them one by one. This slide shows how our DMI is structured and provides a high-level view of all those objects that we configured and created during the demo, running various scripts. So when you run those scripts and look for examples, this hopefully will help to navigate. You can check certain documentation links. And this is just a starting point, a reference to our GitHub account with the demo and Kubernetes documentation, which explains, which is a starting point for the storage management on Kubernetes, and Kubernetes managed site that lists all known CSI drivers. So you can look through them, and pretty much any type of storage available on the market already has a CSI driver. A couple more interesting projects that are not directly related to this topic, but related in some way. So Rook is a controller for storage controller for Kubernetes. So most well-known storage for which Rook provides this Kubernetes adapter and integration is Ceph. So with Rook and Ceph you can provision reliable, scalable storage system directly into your Kubernetes cluster. And as I mentioned in the beginning, we have a whole separate webinar on our website. You can check it in video sections. In the video section that talks about using Rook and Ceph to provide cross-cloud, multi-cloud, mirrored storage system. Velera is a BCDR framework for Kubernetes, pretty much standard de facto for Kubernetes backups, which is also related to storage and uses and integrates many of the features of Kubernetes storage we talked in this presentation. Of course, there are a number of questions that are left out of this. We can talk hours about various aspects and extensions and use cases, etc., etc. They may be subject to other presentations and webinars that we may want to do later. Some of them we already did. And now I think we are open to questions. Let's see if we have anything.
So we do have a few questions. First one being, can Kubernetes synchronize data between the clusters?
Yes, so Kubernetes by itself cannot. but there are frameworks and tools that allow you to do that. Again, going back to our discussion, Ceph and Druk, for example, Ceph allows you to set up mirroring between clusters, between clouds, wherever they are running, or between your data center and the cloud, and your data volumes, persistent volumes, would be mirrored and synchronized. Synchronization can work on higher levels, so if you are using raw storage in each cluster to run, let's say, Vitess cloud native database, you can set up cross-cluster synchronization of the data on the database level. There are a number of other scenarios that you can consider for data synchronization.
Does Kubernetes provide tools for databases and other types of storage similar to what it does for disks?
Yeah, so, and again, yes and no. So Kubernetes itself, core Kubernetes, does not. So core Kubernetes only contains these persistent volume abstractions and persistent volume claim abstraction that are good to represent block storage and file storage, like EBS disks and NFS. But there are a number of tools, add-ons to Kubernetes or frameworks that allow you to manage different types of storage. The same Rook we mentioned not only allows you to manage Ceph as a part of the cluster, but it allows you to manage Cassandra and a few other storage systems. So giving you the higher level controls of different types of storage.
And then the last question we have for the sake of time is, does Kublr provide storage management?
Kublr, okay, so yeah, the question is probably about Kublr. Kublr, again, core Kublr is a Kubernetes management system. But in addition to just creating and managing Kubernetes clusters, Kublr allows you to manage applications running on top of those clusters, including system applications like storage systems, for example, or CSI drivers that integrate those Kubernetes clusters with storage systems that you already have. And in that sense, so Kublr simplifies storage consumption or management of storage consumption components in those Kubernetes clusters.
Awesome. Well, thank you everyone for joining today's webinar. If you haven't already, please complete the survey that is provided in the chat. This helps us to know how to improve and how to know exactly what you guys would like to see in the future. And we hope that you can see us next time. Thank you, Oleg, for such a great webinar.
Thank you. Thank you. Thank you for joining.